I'm Joshua Bardwell, and you're going to learn something today. Today we're talking about load banks. I'm going to build a load bank, and I'm going to make videos documenting the process of me building a load bank. And we're going to start today with a discussion of the decisions you have to make when you spec the parts for building a load bank. If you don't know what a load bank is or why you might want one, we'll talk about that in this video as well. I am going to let you know that this video is not going to have any face camera from me. I'm on a trip right now, and I left my freaking video camera at home, and also I'm in Germany, so my lighting that I usually bring with me doesn't run on 220. So basically, my face cam looks like terrible, and I just will not subject you to that. So you're going to get my voice, and you're going to get my awesome slides. Check out my template, and you're going to get a lot of good information about, well, basically, power distribution and current flow. See, this is actually a video. It's kind of like a primer on Ohm's law in the context of designing a load bank. Let's get into it. A load bank is a device that develops an electrical load, most commonly resistive load. It applies that load to a power source, and then it converts or dissipates the power output from the power source, typically by turning it into heat. So a real-world load might be something like an electric motor, and a battery applies voltage or current across the electric motor, and the motor turns that power into work. It does something with it. A light bulb might light up, a motor might spin and do work. That is a useful load. But a load bank, basically, it's used for testing a power supply, for example. You can see on the slide here, one of the uses is generator test and run-in. So if you want to test that a generator can power your hospital, you're not going to hook it up to the hospital and just crank it up and see how it goes. You're going to test it on some kind of a dummy device. And the load bank is an example of that kind of device. Sometimes a load bank actually is doing something useful, like load banks I've read, I don't know this for sure, but I've read that they're used in trains to brake the electrical motors, not brake B-R-E-A-K, but B-R-A-K, to help stop the train, because the load bank will, it'll apply a load, and if you've got an electric motor or something, dumping that load into the load bank will cause the motor to slow down. But the reason for using a load bank that we're going to focus on in this video is discharging batteries. Now, if you've got a battery discharger, it oftentimes will just consist of a bunch of resistors, and it dumps the power through the resistors, and the resistors convert the electrical power into heat, and there you go. That's how you discharge the battery. And that's why your battery discharger has a fan that gets really loud, because you have to do something with that heat. If you don't get rid of it, it'll stay in the resistors, and they'll get hot, and then something will break. Load banks are also super useful for testing batteries. Let's say I want to test batteries, and I need to discharge 60 amps from the battery. Well, how can I do that in a repeatable way? If I were to just take a motor, and how would I even get 60 amps reliably out of the motor? I would have to control the speed of the motor, too many variables. A load bank will be much more consistent. Of course, the most consistent thing would be a sort of computer-controlled constant current device, but those are expensive and complicated. A load bank is actually reasonably inexpensive to build, depends on how big you want it to be, and pretty simple to build if you understand what you're doing. Two of the things you need to think about when you get ready to build a load bank are, number one, how much current do you want to flow through the load bank? Now, high-end load banks like this West Mountain Radio computerized battery analyzer, they just use computers and electrical components to precisely control the current. So if you're willing to spend $3,000+ on this device, I've really tried to talk myself into figuring out a way that I could afford this, but I just can't. I just don't do enough battery testing to even have to sell a lot of batteries to make this worthwhile. But you just tell it, I want 20 amps, I want 40 amps, I want 60 amps, and it just does it, right? That's a constant current load bank. Great. If you draw too much current, you can damage the power supply. And in the case of LiPo batteries, we know that intimately, because if we're too heavy on the throttle, then what happens? The battery comes down and it's puffed, and we've drawn too much current or too many volts, too low voltage out of the battery. So we don't want to overdraw the current. We want to control the amount, and we need to be able to predict how much current will come out of it. The other thing we need to be concerned about is the watts that are dissipated. And basically, watts equal heat, more or less, in this context. So how hot will each part of the load bank get? And as we said before, energy has to go somewhere. The load bank converts it to heat. But if it gets too hot, well, think about your oven, right? If you have an electric oven, it's got a resistive load. That's the heating element, is what we call it. And it pushes electricity through the heating element, and that electricity is converted to heat. Well, it's kind of like a load bank, except it's actually, in that case, the heat is the actual work that we mean to do. But functionally, it's exactly the same thing. And if the load bank gets too hot, it'll burn itself up. So we need to make sure that we choose parts that can handle the amount of heat that we'll be applying to them. And in order to do that, we have to know how much heat is going to be created when we apply the current. Now, there are two key formulas that you need to know in order to understand the rest of this video. We're going to have some math in this video. Stick with me. I hope you'll hang in there. And the first one is possibly the most important formula in all of electronics. It's Ohm's law. That's the one on the left. And it says that the current, which is measured in amps, flowing through a resistor is equal to the potential, which is volts, applied across the resistor, divided by the resistance, which is ohms, of the resistor. Or to put it another way, I equals V over R. The other formula that's relevant to this discussion is the one on the right, which is P equals V squared over R, which says that the power, which is watts, that's dissipated by a resistor is equal to the potential, which is volts, across the resistor, squared, divided by the resistance, which is ohms, of the resistor. And you see, these two formulas address the two things on this previous slide that we need to know about. Ohm's law will tell us the discharge rate, and the second formula, which is actually just a derivation of Ohm's law, everything is, the second formula tells us the number of watts that are going to be dissipated. So these are the formulas that we will use to answer these two considerations and find out if our load bank is going to work or if it's going to burn itself up. You see, because we need to not burn up our load bank, but also we need to not have a gajillion. We could just buy a gajillion tiny resistors and put a minuscule amount of current through each one of them, and but we'd have a lot of soldering to do, and we'd waste a lot of time and money and space. So we want to have just enough current flowing through the resistors that we make efficient use of our space, our time, and our money, but not so much that we burn them up, and destroy the thing. Now, Ohm's law has many forms, and if you did well in high school algebra, you can see that each of these is just a rearrangement of the others. They're just expressing the same concept algebraically, the same relationship. We can say that current equals voltage divided by resistance, or resistance equals voltage divided by current, or voltage equals current times resistance. These are just rearrangements of the exact same formula. So let's do some examples of applying these formulas. And although this may feel to some of you, or your brain is hurting a little bit right now, some of you are like, yeah, I get it. I know this. I know. Stick with the slower people who haven't already internalized all this. If your brain's hurting a little bit, this is algebra, but it's really very, very simple math. It's just multiplication and division. It's not complicated. Let's go through some examples. How much current will flow through a 1/2 ohm resistor when it is wired across the terminals of a 4S battery? And to answer that question, we use Ohm's law. I equals V over R. I, or current, equals 16.8 volts. That's a fully charged 4-cell battery, divided by 0.5 ohms, or you can just pull out your calculator and do 16.8 divided by 0.5, and you'll get that the current equals 33.6 amps. So if we apply a 1/2 ohm resistor across a 4-cell battery, we'll get 33 amps of current flowing. How much resistance is needed to get 3C of current out of a 1500 milliamp hour battery? Now this actually is vaguely related to the load bank, because when we think about a load bank, we want to pull not too much current that we're going to damage the battery. Now the good news is that the batteries that we use are designed for very high discharge rates. So in fact, you could probably discharge easily at 20C for most batteries. But if you wanted a lower discharge rate, 3C. So 3C out of a 1500 milliamp hour battery, well, 1C would be 1500 milliamps, or 1.5 amps. Multiply that by 3 to get 3C, and you get 4.5 amps. Since your target current is 4.5 amps, we now use this rearrangement of Ohm's law, which is R equals V over I, since R is what we're trying to solve for here. And we say that the resistance that we need to produce that 4.5 amps equals 16.8 volts divided by 4.5 amps, or 3.7 ohms. So a 3.7 ohm resistor applied across a 1500 milliamp hour 4-cell battery. Oh, I didn't specify that in the example. Yeah, it's a 4-cell battery. That was assumed, sorry. A 3.7 ohm resistor applied across a 4-cell battery would give us 4.5 amps of current. How much resistance is needed to get 60 amps of current out of a 4-cell battery for test purposes? Now we're getting back to the load bank question as it directly pertains to my situation. Let's say I want to test a battery and I want to see how the battery performs when you pull 60 amps out of it. Well, I need to choose a resistor size that will give me that result. And it's easy. R equals 16.8 volts divided by 60 amps. Again, going back to this rearrangement of Ohm's law, R equals V over I. We're solving for the resistance, and the answer is 16.8 divided by 60 is 0.28 ohms. So I need a 0.28 ohm resistor to get 60 amps out of a 4-cell battery that's fully charged to 16.8 volts. But here's the key question that makes this all so simple. I'll just go get a 0.28 ohm resistor and I'm good to go. Well, hang on, you're not done yet. Because that resistor is going to, why don't we just get 1,000,000 amps, right? Just take a piece of copper wire and plug it into the terminals of your XT60 on your battery and see, don't do this, don't do that. But see what happens. You'll get sparks and fire and something will melt and the battery will explode because it'll dump hundreds of amps potentially through that wire. So the resistor is resisting the flow of electricity. And it's doing that by converting that energy to heat. Well, how much heat is it creating? To answer that question, we use the other formula, P equals V squared over R, or power equals V squared, voltage squared over resistance. And the power that little 0.25 ohm resistor would need to dissipate is 16.8 volts times 16.8 volts divided by 0.25 ohms, which is 1,128 watts. That's a lot of watts. Think about how hot a 100-watt light bulb gets. Well, now we all have LED bulbs and they don't get very hot. But think about how hot, something putting out 1,100 watts it'll get very hot. And a resistor that can dissipate that much heat, that's actually a pretty complicated problem to solve. But not too complicated. I'm going to show you how to solve it. And the way that we solve it means we have to think about series and parallel resistors. And if we look at this graphic, I've got here three different circuits with a different number of resistors in serial. And serial means they're connected end to end instead of side to side. So as the current has to flow through them, they each resist the flow a little bit more, and that resistance adds up. And what we can see is that in the bottom circuit with only one resistor, the current is flowing very fast and the resistor is red hot. It's having to dissipate a ton of heat because so much current is flowing through it. But as we've added another resistor in series, you can see the current is flowing slower, and because there's less current flowing, there's less heat being dissipated, and the resistors are having to, they're having to dissipate less heat. And then as we add a third resistor in series, there's even less current flowing and the resistors are dissipating even less heat. So when we talk about series resistors, the total resistance through the series resistors is the sum of the individual resistance values. They all add up. Each of these is a 1 ohm resistor. That's why they have those little ones next to them. So this circuit has a total of 3 ohms of resistance. And in fact, this is exactly equivalent to if we had a single 3 ohm resistor. They just add up and they sum. As resistors are added, then the total resistance goes up and the total current goes down, because the more resistance you have, the less current you have per Ohm's law. As resistors are added, total power dissipated goes down as well, because as the current goes down, the power dissipated will go down as well. And as resistors are added, the power dissipated by each individual resistor also goes down, because if you have 1,000 watts flowing through one resistor, that resistor is taking 1,000 watts. If you add a second resistor and it goes down to 500 watts, now not only do you have less current flowing, but you also have more resistors to split the load. So 500 watts split between 2 resistors, each one will take 250 watts. So adding those resistors reduces the power dissipated by each one, but two ways, both by reducing the overall current and by spreading the power over more resistors, so each one takes less. Now this page shows parallel resistors, and with parallel resistors they are added not end to end, but sort of side to side. So it's multiple paths next to each other, it's like instead of having one big long queue, you have 3 or 4 queues right next to each other, right? That's parallel resistors. Calculating the total resistance of a network of parallel resistors is a little bit more complicated. You don't just add them up, and you can see the formula here, but to sum up, what you see is that the more resistors you add, the more current flows. It's like if you are trying, traffic's trying to get through a toll booth on the highway, right? And they open up another lane. More traffic's going to get through. And the more lanes you open up, the more traffic gets through. So when you add resistors in parallel, you're giving an additional path for the electricity to flow. And you can see the example on this other page, over on the right of this page, where when there's a single resistor, current is flowing at a certain speed. And when there are more resistors, more current is flowing. Okay? Now, as resistors are added in parallel, then the total resistance goes down and the total current flow goes up. But here's the interesting part. The total power dissipated goes up because there are more resistors allowing more current to flow, but the power dissipated by each resistor stays the same. Notice that in this example, all of the resistors are the same color. They're all dissipating the same amount of power. So that leads us then to these general guidelines. If you want to dissipate more power, add resistors in parallel, or use lower value resistors. Either of those two things will allow more current to flow, but hang on, those two things are not of equal value. Using lower value resistors will cause more current to flow through those resistors, and they will have to dissipate more power more individually. But adding resistors in parallel doesn't cause each individual resistor to dissipate more power because you've increased the current flow, but you've increased the number of resistors as well. If you're dissipating too much power, add resistors in series, which sort of spreads the load out, or use higher value resistors. So then how do we choose the value of the resistor that we want? Well, number one, you decide how much current you want to flow. Number two, you calculate the necessary resistance value to make that amount of current flow. And then number three, you calculate the power that has to be dissipated by that resistor. So for example, if we want to test a 4-cell battery at 60 amps, we use Ohm's law. R equals V over I. 16.8 volts divided by 60 amps is 0.28 ohms. So we need a 0.28 ohm resistor to get 60 amps. But will we destroy the resistor by burning it up? P equals volts squared divided by ohms, 16.8 times 16.8 divided by 0.28 gives us 1,008 watts, and that's a problem. Down at the bottom of this slide, I've got a screenshot of an Amazon listing for a very common type of power resistor that's used. It's 0.25 ohms, which is exactly what we want, but look at the power rating, 100 watts. Now, you might think, oh, that's fine. It won't dissipate more than 100 watts. No, no, no. That is a maximum. That's like the red line on your car. When your car's red line says 6,000 RPM, it doesn't mean I won't possibly let you get over this. It means if you go over this, I'm going to destroy myself. Well, actually, modern cars might just prevent you from going over it. But the point is that the power rating on an electrical component is the maximum that you can use, you can pull through it before it just burns itself up and destroys itself. So we got a problem. We need to stay under the power rating of our resistor. How do we do that? The answer is to work backwards from the power rating. So we've got a 100-watt resistor. We're going to now ask, instead of saying how many amps do I want to flow and how many watts does that equate to, we're going to say how many watts can my resistor tolerate and how many amps does that equate to. So 100, we're going to work the same formula, power equals volts squared divided by resistance. We're going to say 100 watts equals 16.8 volts squared divided by resistance. Then we continue to solve that. 16.8 times 16.8 is 282. And then 282 volts squared divided by 100 watts gives us 2.82 ohms. So if we have a 16.8 volt power supply, this tells us that a resistor value of 2.82 ohms will produce 100 watts. How many amps is that, though? I need to know amps because amps is what I'm using when I discharge my battery. I'm thinking in terms of how many amps I'm pulling, not how many watts. So if we know the resistance and we know the voltage, we can then use Ohm's law to derive the amps. We can say that I equals V over R, 16.8 volts divided by 2.82 ohms gives us 6.0 amps. And that process tells us that At 16.8 volts, a 2.82 ohm resistor will produce 6.0 amps of current, that resistor will dissipate 100 watts. And that is all the information we need to then design our load bank, because we know that we can go out and we can buy this resistor in a 2.82 ohm size. Now, in reality, we're not going to find a 2.82 ohm resistor. We may need to buy a 2 ohm, but if we buy a 2 ohm resistor, then we'll be sending more current through it than 2.82 ohms because the resistance is lower, and therefore we'll be dissipating too much power. So we need to actually go up. And it's actually a good guideline. If you've got a 100-watt power resistor here, well, chances are that if you run it at 100 watts for too long, it's probably going to hurt itself. These ratings are often a little ambitious. So maybe it would be better to try to calculate maybe 75 watts or 60 watts just to give yourself a little headroom. So instead of a 2.82 ohm resistor, which doesn't really exist, we could look for a 3 or a 4 ohm resistor, and we could use Ohm's law again to figure out how many amps will be flowing through that resistor and how many watts. Then we add up those resistors in parallel to bring the total current flow up to the desired level. So if one 2.82 ohm resistor produces 6 amps of current, then how many resistors do we need to get 60 amps of current? We need 10 of them. And we just add those up and wire them in parallel, one after the other, just like is shown on this page. We just 1, 2, 3, and we just keep going, 4, 5, 6, 7, 8, 9, 10. Each of those resistors will pass 6 amps. Each of those resistors will dissipate 100 watts, and in total, the circuit will dissipate 60 amps and 1,000 watts. Since the power through each individual resistor remains constant, no additional calculation is needed, and current just scales up or down as we add resistors. And in fact, a circuit like this is very good if you want to have an adjustable output, adjustable load. If you had one resistor, you'd get 6 amps. 2, you'd have 12 amps. 3, you'd have 18 amps. And you could build it with switches or with bullet connectors or something, so you could plug and unplug the resistors to add as many as you needed to get the current flow that you wanted. There are 2 main types of resistors that you're going to see when you go out on the internet and you start searching for power resistors. And by the way, power resistor is the keyword that you want. The typical electrical resistors, like the little kind you see on circuit boards, they're usually rated for 1/4 of a watt, maybe to 1/2 a watt, maybe even as much as a watt, but that's it. They're not designed to dissipate huge amounts of heat or power. So these power resistors are typically rated from 100 to 200 watts apiece. If you might think, well, why don't I just buy a 1,000-watt resistor? And they do exist, but they're super expensive and they're very specialized, and you're generally not going to be able to just buy one. And if you did, it would be really expensive. These resistors that I'm showing you now are actually canonically used to test sound systems. You have an audio amplifier that you want to test, and you don't want to put it into a speaker. You don't want to just crank the speaker to, max volume. So you just use one of these resistors instead to test the audio amplifier. They're typically rated for 100 to 200 watts. This style on the left needs to be mounted to a heatsink. You can see it has little screw holes here. It's designed to be mounted to an aluminum heatsink. So when you think about the cost of using this resistor, you also have to add in the cost of the heat sinks, and you're going to need to do you're typically going to need to drill them out to put the screws in. Maybe you could use self-tapping screws, but you'll still need to drill holes. You'll need to use thermal paste underneath the resistor to get good thermal connection to the heatsink and so on. They're just a little more complicated to use. And they're much smaller than this other kind on the right. And as a result, I'm a little bit suspicious of their watt rating. This one says 200 watts. And I just am suspicious that something so small and so relatively cheap, if you're going to use this kind of resistor, use a good-sized heatsink and use like some kind of forced air, like a fan. Some people even take these resistors and they put them inside like some PVC tubing or metal tubing, and they'll put a fan on the end to blow air through the tube so that as much heat is taken away from the resistor as possible. If you just take this resistor and you run it at 200 watts without taking any precautionary measures, you'll definitely destroy it. Now, these are pretty cheap. Depending on the resistance and the watt rating, these are typically between about $6 and $15. Sometimes, it depends on what you're buying, but they're relatively cheap. This type of resistor on the right is bigger You can't really tell, they're not to scale, but it's bigger, and you can see it's got these little metal feet on it, and it's designed to work without a heatsink, so it's essentially self-contained. Now, I actually have one of these on the way that I intend to test, but it seems to me like since this guy is designed to work without a heatsink, it's more likely that the watt rating is going to be honest, and you'll be able to push it closer to the limit without it hurting itself. That's pure speculation, but yeah, it's not designed to work with a heatsink. I mean, that's obvious. It could probably still benefit from good airflow. Anytime you're doing anything like this, having a fan blowing over, moving air over the load is a good idea. The downside is that this resistor on the right usually costs 35 or 40 bucks, and it's the same 200 watts. So, you can take 2 or 3 of these little resistors, put them on a single heatsink, and still dissipate that heat potentially. Whereas, you're going to need one of these, and you're basically going to be paying a lot more per watt, even when you take into account the cost of the heatsink. But my gut feeling is that if in the long term, one using this type of resistor is going to be more reliable and more consistent. That's just a gut feeling, but that's how I feel. Now, another kind of load that you can use is halogen light bulbs. And you could just go get a bunch of 12-volt, 50-watt bulbs. Hey, guess what? The math is done for you. Amps? Who needs amps? We just know that these bulbs are going to consume about 50 watts. So if you did the math and you know you need 1,000 watts that you get to dissipate, you need 20 of these bulbs. Congratulations, you're done. And you also need this base right here you see on this same page. This is a G8 is the keyword, G8 socket, which is the type of socket for these. You find some way of mounting it up, you plug the bulbs in, and, well, you got one more problem. These are 12-volt bulbs, and unless you're using 3S batteries, if you want to use 4S, you can actually get away with 4S. In my testing, I ran these 12-volt bulbs on 4S without a problem, but when I tried to use a 4S high-volt battery, they popped immediately, 100% of the time, every time. So at 16.8 volts, they were okay, but at like 17 volts, that was it. That 0.2 of a volt was too much. If you need to go above 12 volts, here are some things you can think about. And here are some other things to think about if you decide to use halogen bulbs. Number one, these bulbs produce a lot of light. If you build a 1,000 watt array with 20 of these bulbs, when you use it, it is going to blind you. And it's going to make a lot of heat too, but mostly it's going to blind you. Like you're going to see spots. I'm not exaggerating. So consider, if you decide to go this direction, buying like some kind of aluminum flashing or some kind of aluminum ducting, steel ducting. I say aluminum flashing. It's probably not really aluminum. It's probably steel, sheet steel. Flashing or ducting from the hardware store, put it around them, give it some breathing room, and definitely give it some airflow, but just then you won't see the blinding light. As I said earlier, 12-volt bulbs typically work okay on 4-cell, but not on high-volt 4-cell or higher. So what you can do is, number one, they do make 24-volt versions of these bulbs. Now, the downside of the 24-volt version is that it's rated 50 watts at 24 volts, but at 12 volts, you're going to get less than that. And it's nonlinear. The relationship is nonlinear. So you might think if you get 50 watts at 24 volts, you should get 25 watts at 12 volts. It doesn't work that way. In fact, you need to just experimentally figure out, if you buy 24-volt bulbs, about how many amps are going to flow from a 4-cell battery. And I actually have at the end of this slide my findings, because I built something like this for my battery test setup. What I did, though, is instead of buying 24-volt bulbs, I just took two 12-volt bulbs and wired them in series. And that doubles the resistance, and essentially it's as if you had a 24-volt bulb. So I have two 12-volt bulbs in series, and I have multiples of those in parallel, and that means that I can get 4S easy. Bulbs are not necessarily cost-effective compared to power resistors. If you go and, compared to this green kind of power resistor, everything's cost-effective. But if you actually do the math on the whole project, including having to buy the sockets, all the things you would have to buy to build a resistor network or a load resistor with halogen bulbs versus this kind of resistor, the halogen bulbs actually, they seem like they're going to be cheaper, but they're oftentimes not. The bulbs themselves are cheaper, but and you need a lot more of them because they're only 50 watts a piece, whereas that resistor is 100 to 200 watts, okay? The good side about bulbs is that for a fact that bulbs are designed to run at their full rated wattage. So you show me a resistor and you tell me it's rated at 100 watts. I'm going to be pretty suspicious. Like, is that 100 watts if it's mounted on a heat sink with an Arctic breeze flowing over it and then you can run it at 100 watts? But a light bulb, it's always running at full power. So when a light bulb says it's 50 watts rated, you know it's 50 watts all day long, every day, because that's what light bulbs do. I told you that I would tell you my experience with the amp rating using 24 volt bulbs or two 12 volt bulbs in series. In my experience, if I have three 24 volt bulbs in parallel, I get about 20 amps at 4 cell voltage. So that's about 6 amps per 24 volt bulb. Those are 50 watt bulbs. So if you wanted to start out building something with 24 volt bulbs or two 12 volt bulbs in serial, that's by the 50 watt bulbs, and assume you get about 6 amps per, and that's a good place to start. And we're going to close this video with some general recommendations for wiring. And actually, as this project progresses, I'll make more videos. Like, I'm going to show you. You're like, well, great, you gave us all this theory, but you didn't show us how to actually build it. Yeah, I know. I'm right now I'm working on the theory, and when I get to the point where I'm actually building it, I'll make a video about that too. But don't hold your breath. It'll be a little while before I get to the point where I feel like I have something presentable. But here are some general recommendations for wiring. In my experience doing battery testing, I built my current battery test rig with 12 gauge wire, and I do 60 amp discharges, and I've done 60 amp discharges for 2 hours at a time. Obviously not the whole 2 hours, but one battery after another. And I found that wire got warm, and the XT60 connectors definitely got warm, but it didn't get to the point where it was in danger of melting something or starting a fire. It wasn't even really painful to touch. So although if you go look up an ampacity chart, if you go look up a chart for how many amps can go through how big of a wire, it will tell you that 60 amps is way too much for 12 gauge. But those ampacity charts are really conservative. Therefore, if you're going to put wiring in your car where, you know, it's not like it's a load where you sitting there monitoring it all the time. So I say that 12 gauge wire is okay up to about 60 amps. If you're going to go up to higher numbers, I think you should just bite the bullet. Don't go, well, maybe I'll go from 12 to 10 gauge. 10 gauge, go all the way to 8 gauge, and I feel like that'd be okay up to about 120 amps. That's based on some research that I've done, but you should, obviously, you're in a wild west here. If you build something like this, it's on you. Pay attention to heat buildup and so forth, and, you know, if you burn your house down, that's not my fault. If you have the option to use heavier wire, definitely do it. Because the thinner the wire that you're using, the more volts the wire will drop, and that's why the wire is getting hot. You want the resistors getting hot, not the wire. And especially if you're doing battery testing as opposed to just trying to discharge your freaking batteries, then you really want as many volts. You want a consistency, and having the wire dropping volts is not consistent with that, conducive with that. So use heavier wire if you can. Fine strand silicon wire is best, but if you have the option to use solid core copper wire, it's okay as long as you're not moving anything around very much. Solid core copper wire is fine, except that if you constantly bend and unbend it, it gets brittle and it breaks. If you've got something that's screwed to a board and it's just not going anywhere, you can save some money by using solid core copper instead of fine strand silicon wire. XT60s, obviously, as the name suggests, they're good up to 60 amps, probably a little higher. Eventually, you will melt an XT60, but they're definitely good up to 60 amps and maybe a little more if you give them a little time to cool in between tests. Above 60 amps, there are like XT90 or something connectors. I don't remember what it is, but just at that point, I think go to bullet connectors. If you look at the guys doing, 10S helicopters and stuff, a lot of them are just using bullet connectors. And so like 6mm bullet connectors, I would, based on my research, suggest that they'll be good up to about 120 amps. The other thing you can use is ring terminals. Those are those little, they crimp on or solder onto the end of the wire, and they basically just have a circular ring that you put down over a screw, and you screw a nut on and it holds it down, and that's a common way of doing high current dissipation. Another thing you're definitely going to need is a big old knife switch, so you can feel like a steampunk engineer throwing this knife switch. I got a picture of one down here. And the reason for that is that if you just try and plug in an XT60 and you've got a 40 or 50 amp load connected to it, the rush of current is going to arc, and it's going to definitely burn the connector and maybe even solder or weld the connector together so you can't unplug it. And then when you go to unplug it, you're going to get arcing as well. it's not good. So a knife switch is designed to make and break high current loads, and it's the right tool for the job. You can find them on Amazon for between $5 and $20, and frankly, the coolness of being able to use a knife switch is well worth it. Of course, there are also silicon pieces, that you can get solid state relays and other things, but finding electrical components in the the 120, 200 amp range, they get pretty expensive and they build up a lot of heat, whereas this knife switch is just dead simple and not too expensive. And that is going to bring us to the end of this video. I won't give you black screen though on the way out while I talk us out. At this point, you've got the fundamental math that you need to choose resistors for your load bank. And if you're still here, you really love this topic, you haven't tuned out yet, let me just go to the internet and let's take a look at some of the things that, what's out there. So if I just search on Amazon for power resistor, what do we find? Now look, these little guys are definitely not what we want. It's 100 ohms and it's 10 watts. So 10 watts, if we needed to dissipate, 1,000 watts, right? Then we'd need a lot of them to get to 1,000 watts. We need 100 of them. That's a lot of soldering, and I don't want to do that. Also, there are 100 ohms, and in all of the examples we did, you can see that we're wanting something down in the single-digit ohms. Maybe, depending on how many amps we want to flow, it might be 2 or 3 ohms. It might be a half an ohm or a quarter ohm. It's definitely not 100 ohms. So we could certainly refine our search by saying power resistor 100 watts. And now we've got some 1 ohm, 100 watt resistors. We've got 2 of them for $7. So that's what you could do as you're thinking about this is you can say how many dollars per watt am I paying? That's the key thing, right? So, or dollars per amp if you want to work the math that way. So here we're basically paying $3.50 per 50 watts, okay? And then you could kind of cost compare building this out with different ones. Anyway, that is going to bring us to the end of this video. Thank you for watching. Leave any questions, or if I screwed up the math or got anything wrong, which is definitely a possibility, definitely let me know down in the comments. Thank you for watching, and happy flying.